Grade 12, so you should be ready to apply the knowledge you have about double and compound angles in combination with your reduction formulae to simplify or evaluate or prove left-hand side, right-hand side, pretty much to tackle any sort of trig question. We've covered all the theory now. Now it's all about getting into the nitty-gritty applications. So let's start with evaluating without the use of a calculator, using every bit of knowledge you've accumulated thus far. These examples are taken from exercise 4.5, which is your homework, but I also insist that you please read over the example 7 on page 140 and 141 to get some more in detail explanations. Righty. So first things first, when you look at this question, 2 sine and cos, I hope that what's coming to mind is the double angle identity for sine, because it looks very similar, I'm sure you can tell. But there's a problem. 105 degrees versus 255 degrees. They are not identical. Therefore, we cannot apply the double angle identity straight away. We're going to have to change them up. So you can't randomly just think what to change them into without the very beautiful guidance of the cast diagram. Draw the cast diagram on every single page. 105 degrees falls into quadrant 2. What's another way of writing 105 degrees? We can maybe say 180 minus 75. What about 255 degrees? That's in quadrant 3. So let's rewrite it as 180 plus 75. Now we're getting the same number repeating itself, so we will eventually be able to use that sine double angle identity. Okay, so 180 minus 75 turns our sine into merely sine of 75. And then cos of 180 plus 75 turns that into negative cos 75. Why negative? Because that's tan's quadrant. Cos will be negative in that quadrant. Now, just to make things look a bit neater, I'm going to bring that minus all the way to the front. And voila, we've got the double angle identity right-hand side, just with a little minus in the front. So we just leave that minus there. Like I said in previous lessons, if you're taking the right-hand side of the identity and you're trying to make it look like the left-hand side, you must always be doubling the angles. So that's how we get negative 2 sine 150. I've doubled the 75. What do we do? Back to the cast diagram. 150 lies in quadrant 2, so we can rewrite 150 as 180 minus 30. And because quadrant 2 belongs to sine, we keep sine as is. We don't change any signs. It doesn't become negative. So negative 2 sine stays negative 2 sine 30. And if you don't know by now, check on your calculator what the special angle sine 30 gives us. It's a half, and negative 2 times a half is negative 1. Easy peasy. Next example. Everybody always gets so afraid when they see fractions, but let's just work with one part of this fraction at a time, and eventually, hopefully, things cancel out and we end up with something really, really simple. Now, 40 degrees, and 100 degrees. First thing that must come to mind is, once again, our cast diagram. I'm going to leave the 40 degrees as is because they are acute angles. They fall in quadrant 1. You can't really rewrite them as something, and there's no point in doing that just yet. Let's look at the 100 degrees though. 100 degrees falls in quadrant 2, which means we can replace sine 100 with sine 100 minus 80. And because quadrant 2 is sine's quadrant, it's going to stay positive. We can now replace that and reduce it to sine of 80. What's so special about this? I hope that you're seeing the correlation between 80 degrees and 40 degrees. If we double 40, we get 80. So perhaps we need to use a double angle identity. Now, the numerator of this fraction looks very similar to that double angle identity, but it doesn't have the 2. So let's think about this for a second. How can we transform sine 40 cos 40 into 2 sine 40 cos 40? I say just go for it. Write it down as 2 sine 40 cos 40. And then you allow yourself to look at it and say, okay, if I were to have to cancel out that 2, what would I multiply by? And then you realize it's a half. Hopefully you're getting this by now. I think it's the 3rd time I'm doing an example that's using the cos double angle identity without the 2 in front of it. And another example is coming up as well. So we will reinforce this concept. So now we have 2 sine 40 cos 40 on the right hand side there in the little thought bubble, and we can replace that with the left hand side of the sine double angle identity as sine 80. But just remember that the half is there in the front. So now I have something that I can insert into my numerator of this fraction, and voila, voila, our sine 80s cancel, and we end up with a half as the final answer. Example number 3, still taken from exercise 4.5. We're now on the first question, number 9. This one is so easy peasy. I hope you can get it straight away. If you can, if you'd like to give it a go, press pause and simplify this as far as possible, and then see if you come to this right answer. Otherwise, let's start with that middle term. Why? Because there's a sine and cos next to each other, a matching angle. Once again, I think we need to apply the sine double angle identity. Yes, we do. So, now's a chance to remember. Let's just rewrite this as an identity. I'm repeating the same concept as the previous example, and that is, if you have this double angle identity format but without the 2, just pop a half in front of your sine 2x. It's like dividing by 2 on both sides if you're having a look at these yellow triangles of the identities. So that means in our next line we can replace the middle term over there, sine 22,5 cos 22,5, with a half sine double 22,5, which obviously gives us 45, which is fabulous because that's a special angle. Now let's have a look at these squares that have been left behind. A cos squared 15 minus sine squared 15. Of course, it's the cos double angle identity. So we can replace cos squared 15 minus sine squared 15 with cos of double 15, which is 30. We've got all special angles. Cos 30, sine 45. Just a reminder, the blue squiggle comes from the double angle identity for cos. The gray squiggle came all the way from the top where we use those yellow rectangles, the double identity for sine. Double angle identity, sorry. Now we replace our special angles and simplify. Voila. Voila. And the last little example for the day, really, really simple if you are systematic and logical about your thought processes. If you try to do too much in one go, that's when you run into issues. Let's break this down a little by little, even if it doesn't make sense, even if it's not linear on your page. If you can't write this equals straight away and you first need to let your thoughts bounce around a bit, that's fine. Let's work with the left-hand side of this equation, and once again, we're going to need our cast diagram. Negative 242. Nobody likes negative angles. They don't fall on our cast diagram, so let's make it a positive by adding a revolution to it, and that leaves us with 118 degrees. So we're actually dealing with sine 118, which falls into quadrant 2, which can be rewritten as sine 180 minus 62. Since quadrant 2 belongs to sine, he is positive there, we're actually dealing with sine 62. Now let's move on to the next part of this question. cos 90 minus p. When you see a cos, when you see a 90, change it to sine straight away. 90 minus p is the first quadrant. Everything's always positive there. Beautiful. Last part of this line is cos of negative 329. We don't like negative angles, so we add 360 and we get 31 degrees. Aha, I hope at this stage you're seeing a 62 degrees, seeing a 31 degrees. Double angle identities are going to come into play. Now we can replace each little part with what it's equal to. So do you see this sine 62, the sine p, and the cos 31? Let's sub them into this bad boy. On the left, we have sine 62 is equal to 2 sine p cos 31. What is this replicating? What is this mimicking? It looks exactly like our double angle identity for sine, and hence p must be 31 degrees, just like that.